Okay, in this tutorial we're looking at section 7.8 on related rate problems. So when two or more quantities varying with time are related by some condition, the rates of change are also related. Okay, so when we're doing these types of questions, we need to define the variables, okay, write down the rate that is given, establish the relationship between the variables, write down the rate that needs to be found, and use a chain rule or implicit differentiation to relate the variables. If a quantity has a rate decreasing with respect to time, then the rate is expressed as a negative quantity. Okay, so we'll get stuck into some worked examples. Okay, so worked example 30. Okay, we're saying we've got a circular metal plate is being heated and its radius is increasing at a rate of 2 millimeters per second. Find the rate at which the area of the plate is increasing when the radius is 30 millimeters. Okay. So we know we've got, let R be the radius, okay, would make sense. Okay, T be time, okay, in seconds, okay, and this should be in millimeters. Okay, okay, and then we also need, well, we need to let A be, so A millimeters squared be the area. Okay, at the okay, so we can say that we know that our rate of change of our radius with respect to time, okay, is dr dt, and we're told in the question that that's 2 millimeters per second. Okay, now we know the relationship between R and A, because we know that A equals pi R squared. Okay, we want the rate of change of area of the plate. Okay, so what we want, okay, is we need to find dA dt, okay, and evaluate that when R equals 30. So we want that. Okay, well, we can set up a chain rule and say, well, we know dA dt is going to be equal to dA dr times dr dt. Okay, well, we know dr dt. Okay, we know, we're trying to find dA dt. We can find dA dt. Sorry, dA dr. Okay, because we know that dA dr would have to be the derivative of this with respect to r, which would make it 2 pi r. Okay, so we can put everything that we have now into our equation, okay, and say dA dt is our dA dr, which is 2 pi r, times by dr dt, which is 2. So we can say that's really 4 pi r. Okay, then we can say when r equals 30, okay, then dA dt equals 4 times pi times 30, right, which is 120 pi. Now it's always important to put our units for these questions, millimeters per second. Sorry, millimeters squared per second, that's our area. Okay, so we'll keep moving on. Have a look at worked example 32. Okay, so this time I've got a conical funnel, has a height of 25 centimeters and a radius of 20 centimeters. So what we should do here, okay, is actually draw ourselves a picture. Okay, it could be really good idea to draw a picture so you get an idea of what's going on with these questions. Okay, so we've got a conical funnel. We said the radius is 20 centimeters. Okay, so we know that in there is 20 centimeters, and the height of 25 centimeters. Right, it is positioned so that its axis of so that its axis is vertical and its vertex is downwards. Hence why I've drawn it this way. Oil leaks out through an opening in the vertex at a rate of 4 cubic centimeters per second. find the rate at which the oil level is falling when the height of the oil in the funnel is 5 centimeters. Okay, and okay, so we can say, let's define our variables. We're going to let r equal the radius, okay, in centimeters. We're going to let h equal height, okay, in centimeters. Okay, we know that our volume, our rate of change of volume, dV dt, is minus 4 cubic centimeters per second, because they tell us that in the question. They tell us that we're leaking through the opening at a rate of 4 cubic centimeters per second. Okay, we want to know dH dt. Okay, that's what we were trying to find when our height equals 5. Okay, so if we were to set up a chain rule for this, then we'd say that dH dt, well, that would be our dH on dV times dV on dt. Right? So we need some formula that's going to relate our height, okay, to our volume. Okay, so we know that V, volume of a cone, is 1/3 pi r squared h. Okay, so we're getting there, but the problem that we've got at the moment, okay, is we've got this r in there. Now what we need to do is use similar triangles, because what we can say here, okay, is that we've got similar triangles. Okay, so we can say this bit here is h and this bit there is r. Okay, so our radius compared to our height is 20 over 25, but that ratio is going to be the same for r over h. So we can say that r equals 20h on 25, so r is equal to 4h on 5. If we pop that back in this equation now, we can say that our V equals 1/3 pi times 4h on on 5 squared, times h. So I say that V is equal to, when we do this, it's can simplify, so to 16 pi h cubed over 75. Okay, because we times out, we've got to square our 4, okay, gives us our 16. Okay, square our h, times it by another h, gives us our h cubed. 5 squared is 25, times 3 gives us our 75. Okay, so we need though our dV dH. And say our dV dH. Okay, our 3 comes down the front. Okay, it's going to cancel with our 75 to leave it as 25. So we get 16 pi h squared on 25. Okay, so now we can put together everything we need. So we can say our dH dt is our, now we have though our dV dH. Okay, well we've got dV dH, dH dV is just this flipped over. So we can say it's 25 over 16 pi h squared times our dV dt, which was minus 4. Okay, which means when we do that, okay, we can make it equal to minus 100. Oh, sorry, actually, scratch that. We make it, our 4 can cancel out with our 16 and make it minus 25 over 4 pi h squared. Okay, and then we let h equal our 5 that we wanted. Okay, so our dH dt, our rate of change of height with respect to t, okay, at 5 is minus 25 on 4 pi 5 squared. Okay, 5 squared is 25. It's going to cancel out with our 25 and leave us with 1 over 4 pi, okay, centimeters per second. Because remember, our the HDT is our rate of change of height with respect to time. Okay, so we've got to have our centimetres for our height over our seconds. Okay, so we're getting there. Got one last worked example to go. Okay. So what we've got for this next one, okay, is a ladder 3 metres long, has its top end resting against a vertical wall and its lower end on a horizontal ground. The top of the ladder is slipping down at a constant speed of 0.1 metres per second. Find the rate at which the lower end is moving away from the wall when the lower end is 1 metre from the wall. Okay, so what we're going to do is set up a little diagram here. Okay, so what they do is they think of it something like this. So we've got our ladder there, that's our ladder. Okay, so we could say that this length up there to there, we could say is y. Okay, this length here to here, we could say was x. Okay, and we know our ladder is 3 metres long. Okay, now we know that it's slipping down the wall at a rate of 0.1 metres per second. So we would say that's our dy dt. It's going to be minus 0.1 metres a second because it's slipping down. Okay. Now, if we think Pythag, then think, well, x squared plus y squared equals 3 squared, or x squared plus y squared equals 9. Okay. We want to know, okay, our dx dt. Okay. That's what we're trying to find when x equals 1. Okay, well, we can again set up some equations. We can say our dx dt, right, is going to equal dx dy times dy dt. Okay, well, we know dy dt. Okay, we've got that already. Okay, and we can absolutely work out what dx dy is. Okay, so what we can do is we can rearrange our equation here. Okay, and say, well, y squared equals 9 minus x squared. Okay, so y equals plus or minus the square root of 9 minus x squared. But we can ignore the negative because we know y has to be positive. And just say it's positive 9 minus x squared. Okay. Now, if on an exam or something like that, you would need to actually justify y only using the positive. Okay, and you just say y has to be greater than 0. Okay, if you do something like that, you're justifying it. Okay, so we've got that. Okay, well, we can do our dy dx. Okay, so what we're going to do though is let's write it at our y as 9 minus x squared power half. So our dy dx, using our chain rule, our half comes down the front, times by the derivative of what's in here, which is minus 2x, times that by our 9 minus x squared to the power of negative a half. Okay, a half and our 2 cancel out. Okay, it's going to leave us with negative x on the square root of 9 minus x squared. Okay, so that's our dy dx. So if we want dx dy, it's going to be the opposite. So we've got negative square root of 9 minus x squared over x. Okay, so we can bring everything together now because we know our everything that we need up here now. So we can say our dx dt is our dx dy, our negative root 9 minus x squared on x, okay, times by our dy dt, which is negative 0.1 meters per second. Okay. So we bring that together, okay, and we could say, well, our negative and our negative, okay, cancel out. Timesing by 0.1 is the same as dividing by 10. Okay, so you could write it like that. And we've got to let x equal 1. Okay, so dx dt equals the square root of 9 minus 1 squared over 10 times 1. Means we get the square root of 9 minus 1 is 8 over 10. Okay, which when say, when take out the 4th, okay, which makes it 2 root 2 on 10, which equals root 2 on 5 meters per second. Okay, does it make sense that it's positive? Absolutely. Okay, if this is dropping down, then this is going to be getting bigger. Okay, so it makes sense that this is increasing. Okay, so that's the last worked example we've got. They do have a separate method using implicit differentiation. I'd say have a look at it. Maybe don't get too hung up on it. It is actually a shorter process, but given that all our others are working through this same process, I'd probably stick with your same process if you can. So that's all there is for this tutorial, and in fact that's the end of chapter 7.